This tutorial provides a high-level overview of the isotope dilution mass spectrometry and isotope dilution alpha spectrometry techniques for the determination of concentration or basic activity of chemical constituents in analytical samples. What is isotope dilution? In the simplest terms, isotope dilution is a quantitative technique for elemental analysis that uses isotope ratios or activity ratios to determine the concentration or basic activity of a sample. The technique has many advantages over other approaches for concentration or basic activity determinations. One, it is very accurate and precise, as the technique uses ratio measurements rather than absolute measurements of intensities or energies. The measurement of ratios of intensities or decay energies is up to a factor of 10 better than what can be obtained measuring absolute intensities. Precisions of better than 0.1% relative standard deviation by multi-collector ICP mass spectrometry and better than 0.5% for energy ratios have been achieved. 2. It is immune to analyte losses once the spike and the sample are equilibrated. 3. It is a very sensitive technique with detection limits down to sub-picogram levels for isotope dilution mass spectrometry or IDMS and millibecquerels for isotope dilution alpha spectrometry or IDAS. 4. It is traceable to SI units, the mole in the case of IDMS and the becquerel for IDAS. The term isotope dilution was first used by D. Rittenberg and G. L. Foster in 1940. In their work, they were using the isotope dilution technique for quantifying amino and fatty acids. Although Rittenberg and Foster did coin the term isotope dilution, the scientists responsible for the forerunner of the isotope dilution method were George de Hevesy and Frederick Pineth back in 1923. For which de Hevesy eventually won a Nobel Prize in 1943. The two reported on the inseparability of lead-210 from non-radioactive lead and the use of this mixture as a radiotracer, which they used to analyze the solubility of lead sulfide and lead chromate. Over the next decade, de Hevesy would publish numerous papers on radiotracer methods. The underlying principle of isotope dilution analysis is that mass or activity is conserved upon dilution. The dilution of a radioactive isotope by a non-radioactive or another radioactive isotope of the same element results in reduction of the specific activity, which is the activity per unit volume or mass, of the unknown analyte in a manner proportional to the original specific activity and the amount of analyte, and is therefore conserved. Similarly, when using enriched stable isotopes, the diluted natural isotopic ratio is related to the concentration by the amount and the isotopic composition of the enriched isotope that was added. So how does this work in reality? For the isotope dilution technique, an accurately known amount of an enriched stable or radioactive isotope spike, which is also called a tracer, of an element is mixed with the sample, and the activity ratio or isotope ratio of this mixed sample is what defines the basic activity / concentration. The quantities that are known are the sample mass added to the mixed sample and the sample isotopic ratio, the spike mass added to the mixed sample and the spike isotopic ratio, and the spike concentration and the isotopic ratio of the mixed sample. It is important to know that to achieve accurate results by isotope dilution, the spike must be fully equilibrated with the sample. For isotope dilution alpha spectrometry, again, the activity ratio, which is derived from the decay energy spectrum of the mixed sample as shown in the top right, defines the basic activity of the sample of interest. The following equation shows an example of the determination of the uranium-238 basic activity in a sample using a uranium-232 spike. In this equation, the uranium-238 basic activity in becquerels per gram is derived from the activity ratio of the uranium-238 to uranium-232 in the mixed sample multiplied by the product of the mass of the uranium-232 spike added to the mixed sample times the basic activity of the uranium-232 in the spike, all of which is divided by the mass of the uranium-238 in the sample. To achieve accurate and precise results from the isotope dilution alpha spectrometry technique, there are several requirements that must be fulfilled, corrections applied, and other parameters that should be considered. To achieve accuracy and precision, the following elements are required. The spike material being used must be calibrated or have known basic activity, such as that with a reference material or a certified reference material. And the spike must be in complete radiochemical equilibration with the sample. To achieve this, the sample and spike are typically decomposed to bring the analyte into solution, converted to some oxidation or chemical state, and mixed with the spike. Additionally, all ratios must be corrected for decay, instrument background, procedural blank, and possibly dead time pileup if large signals exist, and detector efficiency. Several other things to consider for optimization of the ratio measurements include assessing the impurities and ingrowth for both the sample and the spike, separating out the element of interest to obtain a clean sample. This helps avoid interferences from other isotopes with similar decay energies, minimizing the sample mass to avoid self-absorption of the alpha particles. For example, an electrodeposited source is typically the preferred method over a neodymium fluoride source preparation as the sample mass is smaller. And finally, using a thin film or air packet to avoid recoil contamination of the detectors. There are several advantages and disadvantages to the isotope dilution alpha spectrometry technique for basic activity quantitation. The advantages are as follows. Quantitative recovery is not required as long as equilibration between the spike and the sample is achieved. The technique is applicable to millibecquerels to becquerel activity ranges. The alpha spectrometry instrumentation is relatively inexpensive, and the technique is capable of resolving some isobaric interferences that are a challenge for mass spectrometry, for example, resolving uranium-238 from plutonium-238. The disadvantage of the technique includes that it is a destructive technique or that the sample is destroyed and cannot be reused. An approximate activity range needs to be known for optimal spiking. In some cases, there is a lack of available isotopic spikes, and spikes are also very expensive, and it is labor intensive. For isotope dilution mass spectrometry, the isotope ratio, which is derived from the mass spectrum of the mixed sample as shown in the figure in the top right, defines the amount of analyte in the sample of interest. The equation here shows an example of the determination of the total amount of uranium in a sample using a uranium-233 spike. In this equation, the uranium total in micrograms is derived from the atomic weight of the uranium in the sample multiplied by the weight of the uranium-233 spike added to the mixed sample and the concentration of the uranium in the spike, all which is multiplied by the atom percent of uranium-233 in the spike minus the product of the atom percent of uranium-238 in the spike multiplied by the measured uranium-233, uranium-238 isotope ratio in the mixed sample. This is then divided by the product of the measured uranium-233, uranium-238 isotope ratio in the mixed sample multiplied by the atom percent of uranium-238 in the natural sample minus the atom percent of uranium-233 in the natural sample. This result would then be divided by the mass of the natural sample to obtain the concentration in micrograms per gram. Similar to isotope dilution alpha spectrometry, to achieve accurate and precise results from the isotope dilution mass spectrometry technique, there are also several requirements that must be fulfilled, corrections applied, as well as other parameters that should be considered. Similar to isotope dilution alpha spectrometry, the spike material being used must be calibrated or have a known amount of analyte, such as associated with reference materials and certified reference materials. The spike must be fully equilibrated with the sample, and the spike and the sample must be in the same chemical form to facilitate equilibration. Additionally, for isotope dilution mass spectrometry, all ratios must be corrected for mass bias or instrumental fractionation, instrument background, procedural blank, and possibly dead time if using multiplier type detectors such as those used with the Thermo Fisher Element 2, and moisture content if measuring solid samples. Several other things to consider for optimization of the ratio measurements include assessing interferences, including polyatomic, molecular, and isobaric interferences. Some examples include hydrides, argides, doubly charged species, isobaric species such as plutonium-238 on uranium-238, etc. Separating out the element of interest is another thing to consider in order to obtain a clean sample. This reduces interferences from other isotopes and species with similar mass. Also, evaluating what the optimal spiking ratio is important for reducing the error magnification. This last consideration is highly dependent on the purity of your spike. The greater the purity of the spike allows for a larger range of spike to sample ratios where the error magnification still remains small. There are several advantages and disadvantages to the isotope dilution mass spectrometry technique for concentration determination. The advantages of the technique are that quantitation recovery is not required as long as equilibration between the spike and sample is achieved. The technique is applicable to a wide range of concentrations ranging from sub-ppb to percent level. It is very accurate and precise, and precisions of better than 0.01% can be achieved. And the technique is capable of resolving some interferences that are a challenge for alpha spectrometry, including being able to resolve the plutonium-239 and plutonium-240 isotopes. Disadvantages of the technique are that it requires calibrated spikes, that it is a destructive technique where the sample is destroyed and cannot be used again. Its approximate concentration needs to be known for optimal spiking. In some cases, there is also a lack of available isotopic spikes, and spikes are very expensive. It is also labor intensive, and it is not applicable to monoisotopic elements. Over the years, there have been questions as to whether the isotope dilution technique is in fact a primary technique. Based on the definition adopted by the Consultative Committee for Amount of Substance, CCQM, in 1998, which states a primary method of measurement is a method having the highest metrological qualities, whose operation can be completely described and understood, and for which a complete uncertainty statement can be written down in terms of SI units, the isotope dilution technique is considered a primary technique. The measurement process is well understood and transparent. A complete measurement equation can be written for the measurement process. A complete uncertainty statement can be written for the measurement process, and this can all be done in SI units. However, the current VIM definition states that a primary method of measurement, which is now referred to as a primary reference measurement procedure, is used to obtain a measurement result without relation to a measurement standard for a quantity of the same kind. For isotope dilution, the spike requires calibration to determine the concentration of the element of interest. If you were to use a standard where the concentration was determined by isotope dilution, this is not acceptable, as there is no independent method being used to make this determination. But a standard determined by an independent technique, such as gravimetry or coulometry, can be used for calibration of the spikes, and this would meet the requirements laid out in the current definition. To learn more about NIST, please go to www.nist.gov.